Last time we had talked about this idea of conditional probability. So we had a multi-stage event where the subsequent stages depended on the previous stages. So as an example of that, let's talk about a simple experiment where we draw two cards from a deck and we are interested in the spades, in the chances of drawing spades. Now, in this experiment, we are not going to replace the cards once we take them out. So in terms of a tree diagram, we are going to partition things in terms of spade or not spade. So in the first round, you could either get a spade or not. And then in the second round, the similar situation happens, spade or not spade. We can extend tree diagrams and we can put in probability values here too. So there are 13 spades in a deck of cards out of 52. Because this is a classical situation where it's equally likely to get a card at random as any other card, we can simply calculate the probability of getting a spade. Now, by the same token, we know that the chances of not getting a spade on draw 1 are 39 by 52. To calculate what's happening in the second round, if we have drawn a spade, that means there is one fewer spade left to draw in the second round. So there are 12 of them left out of a total of 51 cards. Now, similarly, that means there are 39 out of 51 cards that are not spades. In the other branch, when we do not draw a spade on the first card, that means there are still 13 left out of 51, whereas there are 38 non-spade cards left. In the notation that we've been using for conditional probability, the chance of getting a spade on 2, given that you got a spade on 1, is just 12 out of 51. So it depended very much on what happened in the first go-round. Now, the chances of getting a spade on 2 depend on what happened in the first round generally. So the event getting spade on 2, there are two outcomes by which you can get there. Spade on 1 and spade on 2 versus no spade on 1 and spade on 2. Now, these are disjoint events. You can't get a spade and not get a spade on the first card. So by the probability axioms, you can simply add these two probabilities. And what's nice about the tree diagram is that it will tell you how to get them. So this first probability, it's a multiplication rule. It's a two-stage rule. It would be 13 out of 52 times 12 out of 51 because it's sequential, and we talked about the multiplication rule last time. And on the second branch, it would be 39 out of 52 times 13 out of 51. Now, in each of these, there's a common factor of 13 out of 52. And if I remove it, what I'm left with is a probability of 13 out of 52, because 12 plus 39 gives me 51. And so the point here is that drawing a spade on 2, the probability of that is not the same as drawing a spade on 2, given that you've got one on spade on 1. Okay, so those are not equal. And I'm doing this partly as a review of the ideas that we talked about before, but partly to try to motivate the next situation. There are some cases, or there are some experiments that have no memory of what happened in the previous stages. So there are no memory of the results in previous stages. The example I did before, when you draw a card from a deck and you don't put it back, the deck remembers what happens because it's missing a card. But as a contrasting example, if we draw two cards and we have replacement, so we put the card back in, we can talk about spades again. And so what's going to happen is our tree diagram will look the same in terms of the number and the types of outcomes. We'll partition it with spade and not spade in each stage. But the values are going to change now. So the first stage of the experiment is the same as it was before. You have a full set of cards, 13 of them are spades, 39 of them are not, so it's a classical probability. But as soon as I replace the card, the next stage resets. And then everything turns out to be the same as it was before. And what that means is that when we ask a question like, what is the probability of getting spade on 2 given that I got it on 1? That situation is very simple. It doesn't care. It's 13 out of 52. Because you reset the deck, there's no issue. For comparison, now, if we wanted to talk about the event spade on 2 generally, remember that it comes from spade on 2 and 1, in addition to the outcome spade on 2, but not on 1. And that was just from what we had done earlier. If we track the 2 branches, that top one will end up giving me a 13 out of 52 times a 13 out of 52 by the multiplication rule. Whereas the second one will give me a 39 out of 52 times a 13 out of 52. And because these are being added, I can see that there's a common factor of 13 out of 52. And once I factor it out, this will end up giving me a 1. So I'll get a 13 out of 52. And the point here is that the probability of getting a spade on 2 is exactly the same as the probability of getting a spade on 2 given that you got one on 1. They are the same. So it's this lack of memory that resets the whole deck here. And we are going to use this to define a new concept. So we're going to use this to define what we call independent events, where the events do not care about what happened previously. But mathematically, we are going to say that events A and then B are independent if the probability of getting B is exactly the same as probability of getting B given that you got A. It doesn't care about what happened on A. And it follows from this and the definition of conditional probability. Remember that conditional probability said, look, things are happening sequentially, so you should calculate it like this. If you make this replacement in here, what you'll find is that P of B gets to go upstairs, and this formula can be rewritten very conveniently as the following. P of A times P of B is how you get the probability of this intersection. So this is kind of what I will call the working definition of independent events. This is the one that you're going to get a lot of mileage out of. So it's another way to write the multiplication rule for independent sequential events. And the simplest example of this is if you flip a coin twice. Coins have no memory of what happened in the previous flip. So if you flip a coin and you get heads, the coin effectively resets. It doesn't care about what you got the first time. It doesn't care if you get 12 heads in a row. It doesn't deliberately try to give you a tails. So at each stage, the probability is just 1/2. So if you were asked to get the probability of heads once and then again, because it's independent, this multiplication rule just simply works out to multiplying the probability at each stage. So it's very, very simple. Now, finally, you can generalize this to many independent events. So if A1, A2, all the way down to AN are independent events, the probability of getting them sequentially is just the product of each probability at each stage. So it becomes very, very simple to calculate.